In this problem, I have a specimen. It's half-inch diameter. Okay, it's loaded with 19.8 kips. That's 19,800 pounds. At and at angle, I want to find the normal and shear stress on that angle that it fractures at. So the first thing I need to do is find the normal and shear force that is occurring at that load. So we're going to go ahead and draw this guy like so. Okay. And again, what I've got here is I've got 19,800 pounds of an axial load. Now, my normal force on this guy is going to be up in this direction, and my shear force is going to be in that direction, right? Because that's the way that the inclined plane. So basically, I have to, rather than have the normal force in line with the axial load, it's at that angle that I'm trying to figure out right there. And again, this angle right here is 52 degrees. Okay, so again, the first thing I need to do is find those internal loads, and I'm going to do that by summing the forces in the x direction. So I've got the 19,800 minus the v cosine 52 minus n sine of 52 equals 0. That's some of the forces in the x direction, right? Because again, that v and n, the shear and the normal, are at an angle with one another. Now I can do the same thing in the y direction. I don't have any force in the y direction and the external force, so I just have those two internal ones, which are going to be n cosine 52 minus v sine 52 equals 0, right? So I just do the statics on this at that angle to find the normal and the shear at the break angle of that piece there. So through algebra, I'll let you do that on your own. I can find that that normal force is 15,603 pounds, and the shear force is 12,190 pounds. Okay, so now that I have those shear and normal forces, I can now go ahead and figure out the shear stress and normal stress just by dividing by the area. Now, the problem is now when you have this at an angle, right? So if let me just draw a quick triangle here, right? So that's 52 like that, right? Okay, and I know this is 0.5. That's the diameter of the thing. When I make that cut, I actually have kind of an elongated ellipse, right? Where in this direction, it's 0.5, right? Kind of in the depth of this. But that elongated, right, is essentially the same as that dimension there, is this dimension here, right? And that dimension right there, okay, if I call that, let's go ahead and call that A, right? Then the sine of 52 then becomes 0.5 all over A, which tells me that A equals 0.6345. So again, what happens is when you cut it at that angle, it's not a circle anymore, right? You've got this elongated side, you become an ellipse. The longer side of that ellipse is 0.6345 rather than 0.5. It's a little bit longer, right? So when I find that area, it's not just the area of a circle now, it's the area of an ellipse. So when I go and do my normal force, which is nothing more than my normal force divided by my area, right? My normal force is 15,603. I just calculated that in the first part of the problem. And then my area, if you don't remember the area of the ellipse, it's basically pi times the short radius times the long radius. So it's going to be pi times 0.5 over 2 times 0.6345 over 2. That's the area of ellipse. It's, it's like pi r squared, but I've got two different r's, right? So if it was a circle, it'd be pi times r, right? Anyway, from that, I calculate that my normal force then is 62,618 pounds per square inch. Or I could do 62.3 KSI if I wanted to. Do the same thing for my shear force. This one is just going to be the shear force divided by the area. Okay. So for this one, I have the 12,190 divided by, again, pi, the same thing. Could have gone through and calculated it and just written that down, but I didn't. So I'll just do it again. It's the same area, just a shear force instead of the normal force. And then that becomes 48,923, and that's PSI. And again, you could always do 48.9 KSI. So again, same idea. You find the internal loads, here being the normal and the shear force, but again, I have to do that in an angle. You use statics to figure that out. Once you have those, you just divide it by the area. A little bit tricky to find the area of this guy, but again, same sort of process on this one.